Hello and welcome back to another Calculus 3 multivariable calculus video. Today we're going to be going over triple integrals and cylindrical coordinates. So the first question we got to ask is what and why, I suppose. Well, what is it? Well, it's changing coordinate system of triple integrals. Pretty similar to what we did in polar coordinates with our double integrals, actually. Maybe more similar than I'm leading on right now, but I guess that's kind of the what we are going to be doing is, once again, we're just going to be changing our coordinate system into cylindrical coordinates. Why would we do this? Well, it's in order to make integrals simpler. Like I said, this is similar to polar and double integrals, and once again, maybe I'm not letting on enough right now why it's so similar, but I guess we'll see in just a minute. But some of these integrals that we're going to be evaluating in triple integrals they're going to get pretty difficult, right? And whenever we can, well, obviously we're going to want to make them easier, right? Less algebraic errors, less errors in general. So that's why we're going to be doing it. So I guess how now is the question. So why is it so similar to polar in our double integral context? Well, it's because it's quite literally a pretty similar coordinate system, actually. So we're pretty much adopting that polar coordinate that we kind of talked about earlier, wherein we have some r radius and a theta off of the x-axis, and that'll coordinate to a point in the xy plane, right? Well, if we coordinate this x point in the xy plane and then just translate it up some value z, that's going to be our cylindrical coordinate system, right? So it's pretty much polar coordinates, but in 3D. We recognize the polar coordinate in the xy plane, and then we just extend it up or down, whatever, some z value to get a point, right? So that's what our coordinate system is going to look like. It's pretty much going to be r theta z. So a couple of bounds, perhaps, that we might want to know is, well, we're familiar with the bounds in our polar. Well, it's 0 is less than r is less than infinity. Well, maybe not a less than or equal to. I guess this would just be a less than. Technically, I think. Anyway, why, I guess, is the question. Well, the radius always starts at the origin, right? I mean, regardless, or wherever we're starting from, that's where the r starts in our polar. So, that's going to be limited to 0, and then infinity, well, this can be however long we want, right? I mean, that's pretty intuitive there. Our theta is going to go from 0 to 2 pi. That's just going to be a circle. Once again, can we do more? Yeah, I guess so. You might be making your job a little bit more difficult, but strictly speaking, the only coordinates that you're really going to need are from 0 to 2 pi. We can represent quarter circles, half circles, 3/4 circles, whatever. We can represent however much of a circle or anything that we want with that. Theta goes from 0 to 2 pi. So those are our polar coordinate kind of bounds, but what are our bounds on z? Well, once again, there's not really bounded. I mean, it goes from negative infinity to infinity. We can recognize any point with our r theta and the z, right? Any point in the z-axis we can represent with rz, essentially with our polar coordinates. So that's going to be going from negative infinity to infinity. So essentially what you can think of this coordinate system is it's just polar plus height is essentially how you can think of it. So we're going to be pretty familiar with this already because we already discussed this in double integrals. So how are we going to convert it? Well, it's the exact same thing as last time. Well, we're going to have x is equal to r cosine theta. That's something that we knew. Y is equal to r sine theta. X squared plus y squared is equal to r squared. Those are all transformations that we got used to prior, right? And then how are we going to convert the z? Well, the short answer is we're not, right? I mean, z is just going to equal z. It's pretty true to what exactly it is. It's the height. We don't need to have a conversion for z, right? That's pretty nice. So I guess that's kind of the point picture, but we kind of need to get into like a function picture, right? To understand how we're going to be doing this. And this is definitely going to be a more intricate example than we're going to be running into. But I suppose that doesn't make it any more different. This right here, I talked about this very briefly in our double integrals and polar coordinates video, but this is a polar rectangle. It's a little bit more of an intricate polar rectangle, but it's a polar rectangle nevertheless. So obviously, when we're having a polar rectangle in the xy plane, where we're going to have two different r values, and we're going to have two different angle values. That is going to be our polar rectangle. While our upper r value is going to be our h of theta right here, and our lower is going to be our g of theta. And then obviously our longer angle right there is going to be beta, shorter alpha. So that's our polar rectangle in the strictly two-dimensional sense. But if we're extending that into 3 dimensions, well, okay, let's just say we have some region D that we want to solve for bounded by 2 z functions, right? These z functions follow the polar rectangle kind of shape if we smush them down into 2 dimensions. That's something that I'm going to be talking about a lot whenever we're doing triple integrals. They're just like metaphorically squishing these functions down. Well, if we squish these functions down, well, then it's going to look like a polar rectangle, meaning what? Meaning that we can essentially use our cylindrical coordinates here. Well, our upper bound is going to be our h of xy, our capital H, I guess, and our lower bound is going to be our z is equal to g of xy. So how are we going to compute the volume of that D? Well, we're going to have the triple integrated integral, iterated integral, I apologize, of xyz. Well, that's just going to be 1 dv if we're trying to calculate the volume here. So how are we going to represent this triple iterated integral in cylindrical coordinates? Well, spoiler alert right here. Well, let's just go ahead and go through this kind of together here. Well, we're going to have that transformation of f of r cosine r sine theta z. We're going to want to transform our integrand into those cylindrical coordinates right there using our transformations right there. R dz dr d theta, we're essentially keeping that r dr d theta that we were talking about when we were doing polar coordinates. That is going to be, once again, very essential when we're doing these. You cannot forget that. We're just going to be plopping into dz now since we have a third integral. So we're going to be integrating our dz first. Well, where does our range go from our dz if we're trying to find our region D in between these two? Well, we're going to pop in right here at our g of xy and exit up here at our h of xy. So those are going to be our bounds right there, g of xy and h of xy. And as for our next differential, r, well, what does our r go from? Looking from a strictly two-dimensional perspective here, it's going to be coming from this right here up to there, right? That's going to be our bounds. So it's entering at our lower bound and exiting at our upper bound. So it's going to be our lower bound and looking like it's going to be g of theta, and our upper bound is going to be h of theta, as we can see right here. Once again, this is a more difficult example than we may be used to. So I guess now we're kind of looking at, once again, in that xy plane, what are we integrating over here? Well, we're going to be having this value minus this value to get this value, right? So our upper bound is going to be the larger of the two because we're going to have to subtract that. So f of the upper bound minus f of the lower bound is going to give us our values. So to get this, well, we're going to have our beta be our upper bound and our alpha be our lower bound. So that would be a polar rectangle, and that's just kind of talking about a little bit of how we might set it up. Once again, this is definitely a more difficult example than you're probably going to be working with when you're doing cylindrical coordinates in this class. But I feel like this was kind of like a motivating thing. Like exactly how would this be easier? Well, to be honest, I don't even know how I would begin to integrate this if this was in Cartesian, right? I don't know what I would even start with, to tell you the truth. The z values may be pretty simple, but beyond that, it looks pretty difficult, if doable at all. So that is how we are going to be switching into cylindrical coordinates. Didn't mean to scare anybody with this kind of example here, but yeah. So I guess let's just go ahead and get into our first example here. We're asked to find the raw volume of region D bounded by z is equal to x squared plus y squared and z is equal to 8 minus x squared minus y squared. So I kind of drew that here. Not really much to say about the drawing itself, to be honest. I just drew that there to kind of get it out of the way. You know what I'm saying? Just so we could grab this if we really wanted to. It's just a matter of whether or not we want to tell you the honest truth. So I guess without further ado, this is our motivating example, perhaps like in an actual application. How are we going to do this in Cartesian? Well, let's just go ahead and follow our usual steps here. Looking at the order, honestly, there's no order that is going to be easier than the other. So I'm just going to go ahead and start off with, well, how are we going to solve for our volume here? Well, it'd be the V is equal to triple iterated integral dV. Let's see, what order? I'll just stick with the regular order, dz, dy, dx. So I guess looking at our z differential bounds, what are we looking at here? Well, we're going to be coming from this z is equal to x squared plus y squared, and we're going to be exiting at the top right there. That is going to be our blue function, z is equal to 8 minus x squared minus y squared. So those are going to be our z bounds, perhaps a little bit uglier than I might care for, but it's doable so far. It's definitely could be a little bit ugly, but it's definitely doable so far. All right, well, smushing this down in the xy plane, I kind of already have that there. Where are we going to be coming in from and exiting from? Well, let's see. If we do our dy, then we're going to be coming from anywhere around this bound right there to over here, right? So what is this going to be? Looks like this lower bound is going to be the upper half of this kind of x squared plus y squared is equal to well, if we smush this down, this will be 4, right? So this is going to be a radius of 2 all around. -2, -2. So I guess this would be 4 is equal to x squared plus y squared is equal to 4. I digress. Well, how are we going to do this in the y? Well, we're going to want to set our y equal to it. So algebraically, it'd be y is equal to the square root of 4 minus x squared. And we're going from the lower half of that to the upper half. So it's going to be negative square root of 4 minus x squared to the square root of 4 minus x squared. And I'll tell you something right now, you lost me there already. I mean, yeah, and I guess we might as well just finish this off right here. Our bounds on x are just going to be negative 2 to 2. So that's pretty simple, I guess. That's the good news. But in Cartesian coordinates, this really does look like a pain. It doesn't look like it'd be very nice to integrate, and honestly, it's probably very prone to a bunch of algebraic errors. So, well, with our new skills, let's go ahead and convert this to cylindrical here. I'm going to use a new color. I'm going to have to change my color on this one. Let's see, what color do we do? I'll do like an orange. Okay. Well, cylindrical, we know our cylindrical is r theta z. So then how are we going to do the volume here? Well, it's going to be the volume is equal to some triple iterated integral of dr, d theta, dz. Switching the order there, I guess. Maybe I shouldn't have done it that order. r, dz, dr, d theta. All right, well, we're integrating in our z first, so let's just go ahead and see what our z is going to be. Well, although that might not be much different, well, what is this going from? Well, we can honestly just, since we already did it in Cartesian, we can just use our cylindrical kind of transformation to turn it into cylindrical coordinates. So, well, what are we going to be using here? Well, we know that x squared plus y squared is equal to r. So if our lower bound is z is equal to x squared plus y squared, well, we can just rewrite that as z is equal to r squared. And similarly up here, z is equal to 8 minus x squared minus y squared. Well, what is that just equal to? I guess that's just going to be equal to z is equal to 8 minus x squared plus y squared. And that's just going to be 8 minus r squared using this transformation right here. Already this is looking a lot easier. Just with our first bound, well, let's see if that's true. Well, what are our bounds on r? Well, we know that r is always going to start at 0, right? I mean, that's really unavoidable. Let me make sure I know what I'm doing here. Okay. Well, we know our r is going to start at 0. Well, what's our radius here? Our radius is just going to be 2 all the way around. So we're going from 0 to 2 all the way around, right? Pretty interesting there. Looks very simple already. And, you know, since we have a circle, well, what are we starting at? Well, we're starting at theta is equal to 0. And moving all the way around the circle, well, we're going to get a circle 2 pi. So our theta bounds are just going to be from 0 to 2 pi. So I guess the question is now, which one would you rather integrate? This one in red or the one in orange right there? I mean, I think the pretty obvious answer here is the one in orange. So let's just go ahead and evaluate this. This just looks a lot easier, so I guess that's kind of the motivating for why we'd use cylindrical, and honestly, it's not all that crazy to do. And most of the time, we're not going to be asked to draw a region and then they're not going to ask us to draw the region and then do it in Cartesian and then turn it into cylindrical. Usually, we're going to just be given this right here, and we're going to look and we're going to be like, oh, this doesn't look very nice. Well, what can I do here? And then we're just going to think, okay, this looks like it's able to be turned to cylindrical coordinates, so you could just turn this into cylindrical here. I digress. That's going to be something that's going to come with more practice, I suppose. But let's just go ahead and integrate this. So we're going to have our volume is equal to 0 to 2 pi, 0 to 2. And then, well, what's r dz? It's just going to be rz from z is equal to r squared. And z is equal to 8 minus r squared, dr d theta. So then coming down, it's going to be v is equal to 0 to 2 pi, 0 to 2. Let's go ahead and simplify this. What is this going to simplify into? Well, that's going to be r times 8 minus r squared. So then that's going to be 8r minus r cubed minus r times r squared. So that's going to be minus r cubed dr d theta. Looks like we're about to run out of room here already, surprisingly enough. Well, we're just going to simplify this a little bit. Oops, messed up right there. This is going to be 8r minus 2r cubed dr d theta. We're going to have the integral from 0 to 2 pi of, what is that, 8r squared over 2, so for r squared minus 1/2 r to the 4th from 0 to 2 d theta. We're just going to equal the integral from 0 to 2 pi of, what is that, 4 times 4, that's going to be 16 minus 4, that's 16 minus 8 d theta, which is going to equal the integral from 0 to 2 pi of 8 d theta, which is going to equal 8 theta. From 0 to 2 pi, which is going to equal 16 pi. Look how many steps we did here. Honestly, if I wasn't showing the work all the way, this could have been like maybe 4 steps, to be honest. It could have been 4 different integrals that I was writing down there. Compared to that Cartesian one up there, that would have been a lot more difficult. So I suppose that was our motivating example here. Yeah, that's I guess what we're looking at for cylindrical coordinates. We'll do one more example. We're not going to evaluate it this time, but we are going to set it up because it's very similar to polar coordinates and what we were just doing. Okay. Oh yeah, looking like we're going to be doing the same thing I was doing up there. I guess I kind of misspoke there, I suppose. This is going to be a time where we are going to have to recreate the drawing. Just looking at this, it's doable for sure. That'll be x squared z plus y squared z. That's going to be x cubed plus y squared x. Uh, x cubed 1/2 x cubed y squared minus. It's doable. You could definitely do it, but we're gonna switch to cylindrical for our own purposes here. All right. Well, color coordinating here. How are we gonna recreate our region? Well, we did this in a past video. 0 is gonna be less than z is gonna be less than or equal to x. 0 is less than or equal to y is less than or equal to. Oops, I switched the order here. I was about to say, like, that's not how that works. 0 is less than x, sorry. Square root of 1 minus y squared. And then our third one is going to be -1 is less than y is less than or equal to 1. So I suppose kind of doing this z is equal to x, z is equal to 0. Well, we really don't have to do much for z is equal to 0, but z is equal to x. We're going to have to do something there. As you can see, I pre-made the graph kind of flipped here. We rotated it to the right essentially, so it's the same process, but we're definitely going to want to make sure we're being more careful here. That's what our z is equal to x going to look like, and then obviously we're just bounded in the xy plane, I suppose you could argue. Okay, I guess moving on. X is equal to the square root of 1 minus y squared. What is that saying? Well, we're pretty much just going to have the upper half of a circle here. That's what that is. X is equal to the square root of 1 minus y squared. X squared, yeah, I guess I'll write it down. X is equal to, z is equal to x. X is equal to the square root of 1 minus y squared, which is equal to x squared plus y squared is equal to 1. So I guess we're going to have a radius of 1 here. So it's going to be going from 1 over here to -1, it would look like. And then it looks like it's just going to be a half circle as demonstrated right here. So let's just go ahead and draw our half circle. Oh man, I butchered it already. Well. Okay. And then our y is, well, -1 to 1. We already did that accidentally, I guess. And since, you know, maybe this isn't too clear right now, but like we said earlier, these are just going to be translated up essentially. So, oh man, what does this kind of look like here? It's our favorite shape. Yeah, there we go. That's our favorite shape. We did this in the last video, I believe. This is kind of our weird, I don't even know what you would call this shape. Kind of looks like a enlarged dustpan, perhaps you could argue. I don't know. Anyway, I digress. How are we going to convert this into cylindrical here? Well, we're going to do, well, let's go ahead and transfer the integrand first. I guess the integrand, we're going to have some triple integrated integral. And our integrand is going to be, well, we're going to use that x squared plus y squared is equal to r squared transformation. So that's just going to be r squared times r dz dr d theta. Remember, r dz dr d theta is our differential for cylindrical and polar coordinates, I guess, just minus the dz. Yeah, so that looks like that's going to be our integrand and differential there. So what are our bounds? Well, we're starting off with dz. We're going to go back to my little orange color here. Well, what are we starting off from? Our dz is starting off from, well, z is equal to 0. And what are we ending up at? Well, looks like we're going to be ending up at z is equal to x. But we can't really use that as the problem because, well, there is no x's in our differential, so that's not going to be integratable. So we're going to be using the transformation x is equal to r cosine theta. So this is essentially saying our z value is going from 0 to r cosine theta. Okay. Now it's time for the easy part here. The z is definitely the most difficult part in all of these problems. Well, what's our radius? Well, we know that our radius is 1 right here. We can see that r squared is equal to 1. So it always starts at 0. It's going to end at 1. So that's our r right there. And what is our theta now? Well, we have a half circle, meaning if we started from over, let's see, I guess over here, this is going to be 0. If we're moving all the way over to over here, well, this is going to be from 0 to pi. That's a half circle right there. So this is going to be our cylindrical integral. As you can see, this probably would have been a lot more difficult if we hadn't done it that way. Well, we would have had from 0 to x. That's not too bad, but once we convert this to the xy plane, then we're going to get some kind of, I think, negative, what is that going to be? Moving from here to here, it would have been, and I guess it still would have been -1 to 1. Regardless, oh, I guess it is right there. Yeah. Anyway, this looks more doable than the last one, I guess you could say. So that is triple integrals in cylindrical coordinates. Definitely helpful in a lot of cases. Also not helpful in a lot of cases, but in the next video we're going to be covering something that is similar to cylindrical, different in a way as well though. Thank you very much.